you the mail I sent to the class. I am going to skip the inference on Bayes network with sampling, and I gave you instead the lectures that you can watch if you're interested. I think it's an extremely important topic, but they're just too many extremely important topics, and you have to classes there. And so I would highly recommend, if you can get a chance, to look at how do you do sampling based inference on Bayes networks. That's something that's very different from logic, because logic you can't do sampling based anything, but probabilities you can, and so it's actually a very useful thing. And in fact, in most cases on Bayes networks, basically the sampling based methods are the ones that we should use rather than the exact inference methods. So it's a useful stuff to know. However, I will see that, and I will go into Bayesian learning, statistical learning, because I just never lost an opportunity to build up Bayesian learning after the semester, and so inshallah should know what it is, and be surprised at how unlearning like Bayesian learning is. In fact, I think if there is one thing that you hopefully will get, you should be able to understand why Bayesian learning is an oxymoron. There is actually no learning in Bayesian learning. It's just inference. And that's something that I hope you will understand. And it turns out that the right way to do learning turns out to be just doing inference, but it's just too costly. So instead, we choose a single hypothesis, and we call choosing a single hypothesis learning. We'll look at that as the class goes on. So another thing that I want to mention before we go forward is that for the final exam, the schedule is that I hope to release the final written take home before Thursday, probably sometime late Wednesday, so right after the last class, and it will be due on Monday, 12/4. Which is basically supposed to be the day of the exam. I set it in such a way so that people who may have made plans thinking that they can skip town after 12/4 don't come and complain to me saying that somehow their travel plans have been affected. So you can be done by 12/4. You can be done in an hour if you want. That's all completely up to you. So that's one part. The second part, as I said, is there's going to be a true-false questionnaire on the blackboard with negative marking. I mentioned this last class. Okay, that would be released sometime before the weekend, and we will set it up in such a way that once you start, you have about a fixed amount of time to complete it. Okay, so it's going to be a huge number of statements, and you have to say whether it's true or false. Okay, and as I said, it will have negative marking. So if you have no clue what you're saying, don't guess, because if you guess, you're likely to not go anywhere, because wrong answers will have negative 0.5 marks, and right answers will have 1 point. Okay, and that's basically to get a sense of the breadth of your understanding of the course, whereas the take-home part will just be the depth of the understanding of mostly the second half of the course. Okay, so that's basically where we are. Are there any further questions before I go forward? Yes. Yes, yeah, it has to be. It will be a. Basically, I will set it in such a way that there is space for all the questions, so it's not like unlimited amount of writing. So it will be like, it looks basically like an in-class exam. So think about it as it's an in-class exam that I'm letting you take. Okay, partly because you haven't had a chance to do separate homeworks for some of the topics. Except it will be a little longer, because essentially I can make sure that you get asked on all the relevant topics. And so the exam will have spaces for each of the questions, and then you just write in the space, and then you give it a hard copy to, basically. In fact, I think if you're giving it on Monday, you just come down to my office, and then I won't be there in my office because I'll be off at NIPS. but you can leave it to one of the TAs and we'll put up a sign where you. Yes.
What's the time limit for the exam?
What?
Time limit? Is there a
For
time
the
limit?
take home?
Yeah.
No, there is no time limit. You just basically have to give it by a certain time that I'll tell you on Monday. So that 12/4 on Monday. 12/4 will basically the day of the exam. Most likely by the end of that day, I will make a sentence. So you have to give it to us in advance. How much time you spend? If you spend all the intervening 5 days just on this exam, or just a couple of minutes on this exam, it's completely up to you. Yes?
How are you getting the written one? It's just going to be online and printed? Or?
Yes.
Okay.
That's what. Yeah.
Does the true and false part have a time limit or no?
True and false will have a time limit. Okay. And again, I'm assuming complete academic code of conduct, academic honor code of conduct. I'm basically, giving you the benefit of doubt that you're all people with, basically academic integrity. But don't make me test the hypothesis. Okay. So in general, that doesn't augur well for anybody who tries to do it. Yes.
What is the percentage split between the true false versus the written?
I'm sorry.
10% is going to be that thing we're hearing tomorrow.
Okay, that's a different thing. So, in addition, there is a 10% force reflections that I assume people have noticed. A whole bunch of you already have. I think about 10 of you have already posted them on the PR. That's a different. Okay. Any other questions? Okay. So we have down to 2 classes basically just this week, and so we're going to, as I said, do Bayesian or statistical learning. So in essence, you can get into this basically saying how do we learn the Bayes networks. We'll get in that way. Although the topics we are talking about are actually much more general, and in fact, you learn some really, really deep ideas in today's class and probably next class. And I think if you understand the idea, for example, of generative versus discriminative models, which will be coming up in the next 2 slides, and you understand the idea of Bayesian learning and approximations to it, map and MLE approximations to it, you understand a lot more than just following New York Times articles about what's going on in the machine. Okay, and so that's something that will come up, but we will get into it basically acting as if, remember we have these Bayes networks, the earthquake, burglary, earthquake, alarm going off, John calls, Mary calls, right? Remember that? So the real question is, can we basically, we assume that somebody gave the topology, we told you how to get the topology if you're putting in, if you have an expert that you can ask about conditional independent assertions, and we also assumed that somebody gave us the CPTs, conditional probability table entries. Right, that's what we assume. And once we have that, we have the model, and then you do the inference, which is basically given any query, figuring out, given any evidence, figuring out the probability that a particular query is true. Okay. Now here is one thing that is very important, and I think I want you to think about this. In this big, burglary, earthquake, alarm, John calls, Mary calls, right? So remember the classification tasks we talked about. I show you an image, and you say it's a cat, or it's a dog, or it is something else. Okay, or I show you a mail and say it's a spam mail. That's a classification task. Right? Now, here in the burglary, earthquake, alarm calls, John calls, Mary calls, I want you to ask the following question. I want you to think about the following question. So, I'm basically, given this, I'm going to be answering questions of the form, what's the posterior distribution of some set of variables given some set of evidence variables? Now, what are the evidence variables that I can give? One of the existing ones, burglary, earthquake, alarm, John calls, Mary calls. What is the query variables I can ask on? Any of the variables. Any of them. So here is the thing that I want you to think about. Are there inputs and outputs in this network? How many of you think there are inputs and outputs in this network? How many of you thought, even for a fleeting second, that there were inputs and outputs in this network? Please work on your mind, get it up. Okay? If you believe there were inputs and outputs, that's because you're believing in the arrow direction. Okay? It's extremely important. I can't, to basically, this is nothing but a joint distribution on 5 variables. Joint distribution on 5 variables. Given this joint distribution, I can say, oh, I happen to know that John has called, earthquake happened. And can you tell me whether Mary will call? Or can you tell me whether burglary happened? Can you tell me whether alarm has gone off? So I can give evidence from some part of the network and ask queries from any other part of the network. Do you see what I'm saying? Now, we talked about this in the context of neural networks. I said there are these feed-forward networks which basically take an input and give the class. And then there were these other networks that we didn't discuss that people used to be very much into, such as Hopfield networks and Boltzmann machines, which are sort of associative in the sense that if you give part of the data, they'll give you the rest of the data. You get this, right? What's in that context, when I'm talking about this Bayes network, is it more like feed-forward network, that there is an input and you get to give the input and it will give you the output. And if you give the output, it doesn't give you the input back. Right? Neural networks, you can't just go to the neural network and say, because I'll make the output be cat, and let's hope for the input to automatically become a cat picture. It doesn't happen. Right? However, if you basically clamp John to call and John calling to yes, alarm to yes, then everything else will essentially have a posterior distribution saying what is their values given this evidence. What's the probability that they'll take different values given this evidence? You see this? This is data completion task. So in some sense, when we're looking at Bayes network learning, in essence, you're essentially learning the entire distribution. You're learning the joint distribution. That's what we're talking about. Once we learn the joint distribution, that is also called, as we'll say in the next slide, generative learning, or a generative model. Okay, so a generative model, there is no difference between inputs and outputs. Okay, you not only care about the class, saying this is a cat, this is a dog, but you also care about the inputs. So if you give parts of the cat and parts of the picture of the cat and say this is going to be the cat, it will give the rest of the picture, or at least give a posterior on the rest of the pixel values. Okay? It's an extremely important idea. So generative model essentially removes the distinction between inputs and outputs. Okay? And furthermore, you have to understand that in Bayes network, there is no inputs and outputs. There are evidence variables. Evidence variables are whatever you happen to observe. That's it. And given those evidence variables, you can compute the posterior on the rest of the variables. Okay? Now, anyway, so I'm trying to learn this Bayes network. So we assume, previously we assumed that the topology and CPT are given. Now what if we want to learn these things from data? If suppose I only have the data about burglaries, earthquakes, John calling, Mary calling, and alarm. I have made some observations about this in my life. Based on this, can I actually compute this network? In a sense, computing this network means looking at the data and learning the joint distribution on the variables. Okay? From a statistical learning point of view, what you are learning is the joint distribution. Once you learn joint distribution, everything else can be answered. Bayes networks are a particular way of compactly representing joint distribution. Do you understand what I'm saying? Okay, keep that in mind. Okay, so it turns out that basically the idea that many of you probably heard about is what's called maximizing the likelihood of the data given the hypothesis. So imagine you consider two different representations for the joint distribution, then you see which representation would have been more likely to produce the data you actually observed, and you assume that must have been the one that actually generated the data. This one is called MLE method. This is what everybody uses, but really we will get to this by first talking about the Bayesian idea, which says I won't make up my mind. I will assume that all possible joint distributions are captured. And there is some kind of a prior on the all possible joint distributions. When I see the data, I update the joint distributions. Each joint distribution is a hypothesis. I update the posterior on the hypothesis. Okay, and so in some sense, at any given point of time, I believe in all hypotheses with differing degrees of belief. Given a new data point, I will essentially complete it, or I essentially give the probability for the new data point by looking at what does this hypothesis H1 say is the probability times the probability of the hypothesis itself, plus H2 says about this data point times the probability of the hypothesis itself, and you will do a huge big summation. I will get to this more slowly, okay, but understand that if you do this, you never make up your mind. So I show you a picture and say, is there a cat in it, a dog in it, or a knob in it, or a hammer in it, or something else in it, and you say yes. You see what I'm saying? There is no learning at all. It's just that you will say, I think there's a little more of probability that there's a cat in it. There's a little less probability that there's a dog in it, etc. Okay, so in general, that's slightly technically wrong, we will get to it in a minute, but essentially the hypothesis that you believe in, that generated the data, you don't just pick one hypothesis. You never pick a single hypothesis. Instead you say, I have a probability of the hypothesis before I saw the data. After I saw the data, I have the posterior of the hypothesis. What that means is hypothesis is just a random variable, just like the rest of the random variables. Burglary, earthquake, alarm, etc. You guys don't care about this. What's the big deal? You don't completely understand what random variables are. You want to call hypothesis also as a random variable. Fine, I don't mind. Blood has been shed in statistics departments just because of this. And these statisticians are mostly sort of quiet bunch, but their religious war really is the hypothesis a random variable or not? When you talk actually about Bayesian statistics, there are a bunch of things about Bayesian statistics. One, of course, is Bayesians make up their own probabilities, okay, subjective probabilities. The second and most important thing turns out to be that Bayesians believe that hypothesis is a random variable. Who are the other guys? Frequentists. Frequentists basically say, no way, hypothesis is not a random variable. Humongous amounts of blood has been spilled because of this. And essentially right now, for the longest time in a statistics department, if you say you're a Bayesian, they'll show you the door and you won't get a job. Right now, all statistics departments are sort of full of Bayesians. So there are like revolutions within revolutions within revolutions. Okay, and so we will understand, for example, this distinction between the hypothesis being a random variable. It's something that you are very happy to believe in because you think everything is a random variable. But how many of you have taken high school AP statistics classes? To the extent you remember, you did frequentist. That's the one where you do p-value action. You don't actually believe that the hypothesis is a random variable at all. You think there is a true hypothesis, so there is nothing random about it. And it turns out that it's actually much simpler to think about hypothesis also being a random variable. And that's what Bayesian is. Really, that's the real difference between Bayesian versus frequentist. Yes?
We still need the expert in this question.
No, actually we know, we're talking about learning, so we basically can have different types of expert, but you don't actually need experts either. So for example, you might say one type of learning is, I will ask the expert for potential topologies. So the expert, let's say, might give the topology, and then I will try to figure out the CPTs. Or I might just figure out both, topology and CPTs myself. Everything from data.
What about the
Prior is a very, very interesting thing. It's actually a very, 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 very good point. The reason frequentists hate Bayesians is because frequentists say there is nothing other than data. There is no such thing as prior on hypothesis. I don't know whether you meant it that way. Prior, if you meant prior on hypothesis, if you meant prior on B and E, that's just CPTs. If you meant prior on the hypothesis, that's a very smart question. And that's actually the reason for the blood spinner. Because if you think hypothesis is a random variable, it should have a prior. Who's going to put a prior on it? Like that Bianchi song, essentially Bayesians put a prior on everything. If they don't have it, I'll just put one. And that's my common sense understanding of where hypotheses are coming from. And it turns out actually putting a prior on the hypothesis can be thought of as background knowledge. You'll see in a minute. Okay? As to certain explanations are more likely than other explanations. In fact, the world is full of this kind of nonsense, right? So, for example, Einstein is particularly good with this. Einstein said, everything should be made as simple as possible, but no simpler. In fact, after he came to US, mostly he was doing this kind of aphorisms. No physics, actually. Okay, right? And so all the people who think they understand Einstein's physics basically understands his aphorisms. Okay, so everything should be made as simple as possible, but more simple. Where do you draw the line? And how did you figure this out? And also Einstein said when he hated quantum mechanics as a way to explain how universe works, that God doesn't play dice. Because he obviously has a private line to God and he talks. Okay, now these are essentially priors on the hypothesis. So he essentially put zero prior on any quantum mechanical hypothesis of the universe and puts non-zero prior on the other hypothesis. Which also, by the way, since you brought this up, it also tells you that in statistics, zero is forever. Zero is forever. In general, in math, zero is forever. In statistics, zero is forever. If you ever put zero on a particular probability in the prior, then how much ever data you see, it will still remain zero. So saying that that's exactly what basically true biases are. So our ancestors basically thought no way is anything other than Earth being in the center of the universe going to be an appropriate model for the universe. So they put zero, big zero, on everything involving any other possibility. And so how much our data comes, they kept making this Earth-centric hypothesis more and more complex, rather than go for the much simpler sun-centric, heliocentric hypothesis. Because you put a zero on the hypothesis. And the priors are your biases. And statisticians tend to believe that, frequent statisticians tend to believe that you are not supposed to have any bias, it should be just data. But it turns out there is no such thing. They have their own kinds of biases, just they don't call it. Okay, yes?
Sorry, can you explain again what you mean when you use the word posterior?
Oh, posterior? Posterior is, so suppose this is B, sorry. So this is B, right? It's a joint random variable. PB is the prior on B. Okay, suppose you actually found out Mary called and John called. Now you want to ask what's the probability burglary happened. That's the posterior. That's it. Basically you always compute posteriors. That's what I said last class, that you can see, you can understand, you can recognize Bayesians by their posteriors. Okay. There's actually a really nice picture of Bayesians and their posteriors, but I won't show you. Okay. Any other questions? Okay. So the next thing I want you to understand is basically generative versus discriminative models. So in essence, there are, let's say, you're trying to model data. What you're trying to do in statistics, in statistical learning, is model data. Data has some variables. Data can be described in terms of some features, x1 all the way up to x100, and y1 all the way up to y100. Typically, you tend to think y are the class variables and x are the input, the rest of the data variables. But there really isn't any difference, actually. So, for example, if I'm trying to model this, burglary, earthquake, John calls, Mary calls, alarm, what are the class variables here? There is no difference between input and output. Everything is a variable that I might want to know the posterior of. In some cases, you tend to think the class variables are slightly different. So, for example, you think, so I want to model your experience over this semester. One variable happens to be your grade. You tend to think, and some of your employers tend to think, that is an output variable. Okay, so if you think that's the thing, then basically you will more likely be asked the posterior and the y variables given x variables. That's the assumption in classification tasks. Okay, in classification tasks, the assumption is that I will show you a picture and I ask you, is there a cat in it? I won't show you half a picture of a cat and say there is cat in it and then ask you to complete the rest of the picture. But that is possible if you are thinking of generative model. In the generative model, I can do anything, essentially, because the name of the picture as well as the pixel values of the picture are all part of the data. Okay, so the most general way to learn anything in statistics is to learn just the joint distribution. So all the variables x and all the variables y, if in fact there is a class variable versus input. Okay, sometimes there is no difference at all, everything is data. Okay, now if I learn this, then if I directly learn this, the entire joint distribution, then I would be doing what's called generative learning or generative models. You keep hearing about generative models as the panacea for everything that is ailing machine learning. And you'll also keep hearing Bayesian learning, the other thing that I'll talk about, as the holy grail. If only we can do it, all the problems with machine learning will be done. So two very important things about machine learning you will get today in the next few slides. Okay, so you want to learn essentially the joint distribution. Okay, but sometimes, if on the other hand, if I tell you, I will only ever ask you the class variables, and I'll only ever give you the x variables, the input variables. Do you understand what I'm saying? If I were to tell you that, you are tempted into thinking, why am I trying to solve the harder problem? Why am I trying to learn the entire data? I need to just predict the class variable. Right? In that case, what you really need to know is this distribution. Conditional distribution, probability of y given x. If you learn the conditional distribution, then you would say you have done discriminative. To some extent, it looks like a reasonable thing to do. Right? I mean, why solve the harder problem than what is needed? Right? There is actually beautiful analogies to everything you do in, like even in exams. If I were to tell you that it's a true-false question, all you need to learn is what is the pattern through the true-false questions that Rao asks. There's a hilarious episode in Simpsons where they are trying to get the class prepared for no child left behind policy, where essentially they have to do well in a certain exam. And so the teacher is telling them, guys, remember A, B, E, A, C. And everybody will say A, B, E, A, C. Because that's the pattern in the answers. And so you just have to write that down. Do you understand what I'm saying? So if they do that, Springfield Elementary would be at the top of the list and they will win. And it would actually be stupid, you might say, to learn anything more than the pattern if you just wanted to pass the exam and nothing else. For example, if you figured out, let's say that in a set of true-false questions, the teacher tends to be kind of crazy about making more false statements than true statements. So 90% of the statements are false and 10% are true. Then you just essentially put 90% of them randomly false. And you do well. And your friends will try to actually read this sentence and try to understand what they're trying to say. They're wasting their time. Why learn more than is needed? Study for the exam. Study for the exam is discriminative learning. So in my class, when I used to have less than hundreds of people in the class, I actually used to have these true-false questions with justifications. You say true or false and you write lies. And I learned a lot more about the craziness of people's brains by reading that. And I always told them that I don't care about, in fact, if you got the right justification but the wrong answer, you get marks. If you got the right answer but the wrong justification, you get 0. That was my negative mark. Okay, so for example, if you say false, because 90% of your questions tend to be false. That's the justification. Say, okay, sorry, this is 0 for you. If I were to make that, if I were to make you give your justification, in essence, to be able to provide the justification, you need to do more generative learning. It's not just enough to specify what the class variable is. You need to actually sort of explain your answer. Okay? So, however, it's important to understand the temptation to do discriminative learning. That's like, why not solve a harder problem than what you're asked to solve? It is true that if you solve the harder problem, if you solve the generative modeling, then discriminative problems are just free. People who understand the entire textbook can answer true and false questions and any questions. But people who only figured out the true and false pattern won't probably understand what's going on in the textbook. Right? Okay. So this part is called discriminative models, and most machine learning techniques that you are normally aware of are discriminative models. So for example, neural networks, feed-forward neural networks are discriminative. Since you guys keep reading all this popular press on neural networks, do you know of any version of neural networks that people keep talking about, which are supposedly generative? GANs. Some people have talked about it. We will, I might mention the connections to GANs later on next class. GANs are generative adversarial networks. In essence,